Swayam Prabha. Digital India. Educated India.
Yeah, thanks to Jitendra for inviting and asking us to talk a little bit on the work we do in our contribution to converting or reducing carbon dioxide emission in the atmosphere. You might have heard I think people speaking on catalytic conversion, maybe also sequestration. I think those kind of talks you would have had. Today I wanted to focus a little bit on electrochemical conversion. It's not new, but it's something which we use exclusively on if you look at hydrogen production. So nowadays there is a lot of talk going on green hydrogen. So that's a process where we tend to use solar energy to power an electrolyzer. So because water splitting is known for ages, it's known since 1800. So it's an area where those days they use electricity, but now since we have solar, we can use a solar or a wind, power the electrolyzer by this renewable energy and use that energy for converting or reducing carbon dioxide. Similar to water splitting, we can do CO2 reduction. So there again, water is reduced, water reduction can happen. So here we try to reduce carbon dioxide into valuable chemicals, and I'm just going to give you a pathway to how we have done this and what kind of products we are getting it, and what are the challenges which we face and how as a student or as a researcher you can address them. That's what I wanted to just give a flavor of the overall process. And just to start, this is a picture. I think you might have been hearing this in the news all the time these days. Delhi is one of the most polluted city in the world, and it happens every winter. There are so many reasons. One is the air movement is there, but other things we have stubble burning in the nearby states, which also bring in a lot of fog and pollution into the capital city, and they are also looking at various ways to mitigate this. But if you look at the CO2 emission is one of the prime reasons why this city is getting polluted, and the levels of CO2 are increasing every winter because of the less dispersion. It's increasing. And this is a picture which is before it's in November 2009. This is just before COVID. They were wearing masks even before COVID. So India mostly, I think they started wearing masks only after COVID, but these pictures are before COVID. And even IIT Delhi, they had they developed a filter just to put it in your nose, so that when you breathe, your air get purified and it can, your lungs are protected. So there are several things were tried in Delhi, and all of that is related to again the air pollution. And India is one of the top countries which emits CO2 next to China and USA, and India has a major contribution in terms of the amount of CO2 being emitted into the atmosphere. And this is the data which shows the world atmospheric concentration of CO2 is exceeded about 410 ppm, or we are close to 410 ppm. That's a kind of not a good sign, because that can result in a global warming, and that is where most of the countries are coming together to reduce that number. At 350 ppm is a good number. That is where people aim to reach to. And also, if you look at where the CO2 is coming from, this is a data from US, but the scenario is similar in every country. There could be slight variation in the percentage. So we have the major contribution coming from transportation industries, and then from the electricity production, and then industrial, commercial use, and agriculture, and so on. So the transportation plays a major role in CO2 emission. That's why if you look at many in Delhi also, a lot of bans were made on old vehicles, particularly diesel vehicles were banned. 15-year-old diesel vehicles were banned, and a lot of encouragement were given to use EVs for a lot of auto rickshaw. The rickshaws are there. The rickshaws were asked to use convert from the IC engine to EVs. So that's a kind of mitigation they looked into. So several things were taken on the transportation industries. At least on India, on the electricity side, we have a lot of renewable energy. I think we are blessed with a lot of sun and wind. So we have a large coastal line, and we also have close to 300 days of sunshine. So our solar energy can be trapped, and we can use them. So electricity can be kind of we are going to close to 50% renewable. So that's one way that's good. But transportation still, most of our vehicles, they run on IC engines, and those are one of the major contributors for this CO2 emission. And if you look at India's commitment in the last Paris Agreement, not only India, I think the world has committed to reduce or keep the temperature below 2 degrees Celsius. That's a commitment we have. And so that requires, several strategies, and it's good to have the CO2 level less than 350 ppm for a better world in which we can reduce the global warming. And so to reduce or to keep the temperature to less than 2 degree or 1.5 degree, there are several things which we can do, so which are listed in here. So we can go for renewables. We can have a good energy conservation, and in transportation we can have electrification. EV vehicles can come into picture. Industry can also go to some amount, use hydrogen as an alternative fuel, or CCS. So here carbon capture and carbon conversion also play a major role in here. So having a technology which can capture or convert carbon dioxide can be a very good option in reducing the overall temperature which the earth is facing. And in that direction, if you look at this is a data just to compare the various car manufacturers, the various manufacturers, Honda, Toyota, you can see whatever you can think of, Volkswagen, all these vehicles are there. So this is the amount of carbon dioxide these vehicles emit for every kilometer they ride. So for example, if you are having a Honda vehicle, you are emitting close to 120 grams of CO2. So every kilometer we travel, so we emit about 120 grams of carbon dioxide into the atmosphere. So different vehicles have different numbers. So they all are in the range of 150 to 200. And so they are also looking at options, how they can effectively reduce this emission. And because a path towards decarbonization, has to have contribution from everybody in the society. So they are looking at other option, the hybrid vehicles are going to electrical, and maybe in the future it can be fuel cells which are powered by hydrogen and so on. So those are some of the pathways which we lead to. But that doesn't mean that IC engine will not be in the market, because that has ruled for close to 150 plus years, and it will always, because petroleum industries, we cannot just like that change to alternatives. And so we still continue to use fossil fuels, and the few things what we can do in with that is, first is to capture CO2. There are various capture technologies. I think some of my colleagues would have talked already. And the other option is conversion. So once you have a CO2 captured, so you can store it, or that's one process, but you can also convert into some other useful chemicals. That's what I'm trying to address in here. So one typical example could be methanol. You can convert carbon dioxide into methanol. So methanol is again a fuel. It can be used as a fuel, and then you can reuse it. You can convert into methane. Methane is natural gas as methane. There are several products are there. You can convert the carbon dioxide into some of these fuels or any chemicals what we need. And there are various ways in which we could do. So we can use conventional homogeneous catalysis, where you mix CO2 with another chemical and you convert into a product. Or we can have heterogeneous catalysis, where you use a catalyst, pass carbon dioxide and convert into product. Or certain enzymes, even photosynthetic process again take CO2 and then convert into starch and glucose and so on. So we have enzymatic process, or a photocatalytic process. You expose that to the sunlight and then you convert that into some useful chemicals. Or we can use the electrocatalytic process. So there are various options which are there, And any technology which can get implemented or it get commercialized, there are a lot of things or tests which we have to address to. It should have good selectivity, it should have good productivity, cost should be low, and it should have recyclability. So a lot of factors which come into picture in here. For example, homogeneous or heterogeneous catalysis, you need high pressure or high temperature for that conversion to happen. And photocatalytic process are very, very slow process. It's it takes a lot of time for any conversion and so on. So each of them has its own merits and demerits. So we are looking here in electrocatalytic process. So the advantage with electrochemical process or the reaction can happen at room temperature. So you can do you don't need high temperature, high pressure. The reaction can happen at ambient condition where you need electricity. And we believe that this electricity can only come from renewable energy. It can be a solar or a wind. So you use them as a storage of your energy. Okay. So room temperature operation is one advantage, and ambient condition, ambient pressure and ambient temperature. And generally, people tend to use aqueous solvents. So you can also use non-aqueous solvents. We can, for example, if you take this Coke bottle. Coke has carbon dioxide. It's a CO2 dissolved in water, some composition they have, and so like that. So we can use Coke, for example, and then you can convert that into methanol or ethanol. That's the process we are looking at. That's okay. So we are addressing or capturing CO2 in an aqueous solution, and then we are converting into some useful products. And whatever I said, we can have a renewable energy to power a device. So device can be this electrolyzer or electrochemical device in which we capture the carbon dioxide from an industry or from a vehicle in some mechanism, and then we pass this, and then you convert that into fuel, and then fuel can again be used in combustion, and then it's kind of a cyclic economy in which CO2 is kept as a player in here, where you try to use it and reuse it so that we can not leave anything into the atmosphere. So that's an idea in which we are looking at. And we can use it as a fuel, and we can also capture it so that the environmental friendliness can come into picture. And from thermodynamics, there are a lot of possibilities in which we can convert carbon dioxide into. So we can convert into formic acid, carbon monoxide. Carbon monoxide in turn can be mixed with hydrogen to form syngas. All the syngas product, you can have syngas for various other chemical production. Methanol, ethanol, formaldehyde, methane, ethane, ethylene. A lot of products in which you can convert, because once you have a carbon, so each of them requires an additional electron. So if you look at the number of electrons required, they keep on increasing as you go higher in the product scenario. For example, carbon dioxide needs if you give 2 electrons, you can get into formic acid, or carbon monoxide. When you have 6 electron transferred, you can get methanol, 8 electron to methane, ethylene, ethanol, and so on. So traditionally in the industrial process, to make formic acid, they use methyl formate hydrolysis, or to make syngas they use coal gasification, or to methane is produced from the natural gas, and steam cracking will be used for ethylene and ethanol. So these are the one which is seen in the red, or the conversion or the current or the conventional industrial process to produce these chemicals. But we can also produce them by electrochemical process, in which, so here in all this case, you need catalyst, high temperature, high pressure, and that's the scenario. You will use energy. Whereas all these chemicals can also be obtained from carbon dioxide by passing just electrons, and these electrons come from solar energy. Okay, that's the things we are looking at. So solar energy, if you look at okay, of course there are some CO2 emission during the manufacturing process, but as a application you don't have any CO2 emission. So you have clean energy, sunlight is transferred into energy, and that energy can be used in the electrolyzer to get all these products. So I think right now we are in a very early stage, but if this technology matures, all your chemicals can be produced from electrochemical process. Yeah. Of course, there are challenges. It's not everything is as simple as it is. We all know that to split water we need about 1.23 volt. Thermodynamically, we have about 1.3 volt you need to apply to split water to produce hydrogen or oxygen and so on. And CO2 on the other hand requires, this is on the negative side, you need about minus 1.9 volt. The first conversion, the CO2 has to get an electron or an ion on a CO2 is converted into CO2 minus. So that requires a lot of energy for the initial conversion. Once you have that process, then you can convert into many of the other products. The standard electrode potentials are given there. So that is the excess voltage where we apply is called as an over potential. For example, water electrolysis should happen theoretically at 1.23 volt, but practically it doesn't happen at 3.23 volt. So you need to give additional energy for this to happen. You might give 1.5 volt or 1.6 volt. So that excess energy is called as an over potential. Okay. Similarly, it can be on the positive side or the negative side. Similarly, on the electrochemical process, you are spending excess energy. Okay, that is what we call as an over potential. Or in other words, we have this. You buy a product from Amazon. So you have a phone, you have some particular weight, but you not only pay for the phone, but for the whole box. You have to pay for the whole box. You can say my phone weight is less, so I only pay for the phone. So you have to pay for the entire. So that excess money, whatever you pay, is called as an over potential we can compare to. So you have to pay that amount. It's not a driving force. Or in other words, the efficiency of an IC engine is about 25%. Practically it has to be 100%, but you are getting 25%. So you have 75% losses in there. So that loss is associated to over potential. Okay. So your complete energy is not utilized. You have a lot of losses. So you have, instead of 1.23 volt or 1.2 volt, your actual electrolysis will happen at about 1.5 volt. So 400 millivolt loss will be there. So that you have excess energy you have to spend. Yeah. So that's over potential. So any material you have to spend more energy. That's what efficiency. The other is Faradic efficiency. That is how much electricity you are sending and how much of that is converting into product. So higher Faradic efficiency is desired. So that's one thing. And the material you should have high current density. Normally high current density will give you more product or a higher product amount of product. Stability is another problem. Any material if you look at water electrolysis, do you know what are the materials which are used in electrolysis? Water splitting, what materials do they use? So it's an anode and a cathode, and what material like? Transition metal, chalcogenized, those are at R&D level, but at a commercial level, R&D level we can try anything. Nephron membrane is a separator, but you have two electrodes. Like a battery, you have an anode and a cathode. Platinum is correct, one of the electrodes. The other one is iridium. Okay, platinum and iridium oxide is used. Okay, so those are noble metals, very expensive metals. Why electrolysis? If you look at the worldwide hydrogen production, so only about 4 to 5% is produced by electrolysis process, because it's an expensive process compared to SMR or the other process. It's very expensive. So because we use a very expensive catalyst in there. So similarly, the stability is an issue, because if you look at the reaction, so we have an aqueous solution. That means there is always water presence is there, and you are applying a voltage. So there is a high voltage is there that will make any metal subject to corrosion, because if you see go outside and see any structure, if you have iron, it will be corroded. Okay, any metal, most metal, if you stay for a long time, it will get corroded. But here we have all the condition to make it corrode, because you have potential, you have aqueous solutions, you have a slight, in India if you have a slight higher temperature, 30-35 degrees Celsius is there. So any material will corrode. And also for reduction you need protons. Protons are nothing but acids. H plus is there, protons are there. So you use some material, they can corrode. That's one limitations we have. That's why in electrolysis platinum and iridium are used, because they are noble metals which doesn't get corrode that easily. Whereas here, yeah, we have a little leverage. We can use other materials as well. That's where we are looking into. So stability is a major issue in electrochemical process. Okay, and challenges are because it's a competitive reaction. When you reduce CO2, you will also produce hydrogen. So the energy you are supplying is used for hydrogen production as well as for your CO2 reduction. So there is a competing reaction is there. You need to suppress hydrogen production. So that's because this starts at 0 volt. This happens much low after that. So you will have this as a byproduct in always in the CO2 reduction. So that is something which we have to take care. So we need to reduce hydrogen evolution. Other problem is the solubility of CO2. How much CO2 is soluble in water? Do you have any idea? If you take a Coke can, it is stored in a cold environment. Do you know why? Solubility of CO2 in water. Some numbers you can give. How much CO2 can be dissolved in water? Some X grams per liter. Some numbers you can throw. It's okay. Yeah,
1.45 gram per liter.
How much?
1.45 gram per liter.
1.45. Yeah, not bad. Yeah.
Should be less than 10 grams.
Correct. Yeah, less than 10, little more than 1. 1.45 is accurate. It's a very precise number. Yeah, okay.
Amines it is 700 grams.
Yeah, amines are slightly different, but in aqueous solution.
Water is like less than.
Yeah. So it's about 3.5 grams. So 3.5 grams. So if you have 1 liter of water, you can only dissolve about 3.5 grams at 0 degrees Celsius, like that too at 0. If you go to, that's why your Coke can is always stored at a little lower temperature. And once you release it, you can see the CO2 coming out and so on. So carbon dioxide has low solubility in water. You can use aqueous non-aqueous solution, but that has its own disadvantage. I'll talk about it later. So then selectivity, because when you try to convert carbon dioxide into any fuel, you will not just get one product. You will have n number of products. So how do you selectively remove or you improve the selectivity of a product? So that's a big challenge we have in here. And stability, of course, this is an issue which we have. So these are some of the challenges which are there when we convert carbon dioxide into chemicals. But theoretically, yeah, this is what you have the scenario where you can convert. If you are able to convert pass 2 electrons, you can get one of these products, 6 electron, 8 electron, depending on the number of electrons you transfer to CO2. You can get any of this product. So that's a theoretical one, but practically there are limitations which are there. Yeah. So how it is done in the lab scale and how electrochemical reactors are put together. So this is what we call as an H cell, which is we generally use in the lab. So there are different configurations are there. I'll talk about a couple of them. So this is nothing but you have two, it's similar to a battery. You have an anode and a cathode, then you have a separator which is separating these two. We are passing carbon dioxide into one of these chambers. You saturate until it's completely dissolved, and then you apply a potential. So you have two electrodes, we call as a working electrode and a counter electrode. Okay, you apply a potential. So here cathode, there is a reduction reaction which happens, so that will reduce the carbon dioxide into product. That's the thing which will happen. And to know how much voltage you are applying, we keep a reference. A reference electrode is like a referee in your cricket or a football match. So it's there just to see, whether you are applying the right voltage or not. So you have two electrodes. This reduction will happen. Similarly, oxidation will happen on the anode side. Usually, it's water oxidation. Water will oxidize to oxygen, and here CO2 will reduce to some product. So this is how traditionally it will happen. And over the years, we have changed configuration just to make it, we have gas diffusion layer. If you are passing gas, or you can have this is brought together to make it like an electrolyzer, where you just have CO2 passed on one side, and you have a membrane which is separating a anode and a cathode. Like there's a different configuration which has come, but let's look at just a simple configuration, and we'll look at some data from our lab. So initial experiments, what we have done is, so this material we have taken as copper. So this material is a working electrode, what we call. We have taken a copper strip. So we have passed carbon dioxide, and then we are able to apply a potential to reduce carbon dioxide. So this is a pure copper, and then we also deposited this by some more copper just to increase, because in catalysis, higher material you have, you will have more products. So here we are trying to increase the surface area of the copper by depositing some more copper on it. Like you have an house and you are building an apartment over it. Okay, so you have more people can live in. So you are depositing more and more copper on it, and then you are using for a conversion. And this is the, so in this case we are able to identify some hydrocarbons, like we have methane and ethane. So this is ethane and this is methane. So over a function of time, are able to get about 150 micromoles of methane. And the blue one you see is a hydrogen. So we have more hydrogen as well, because hydrogen is a byproduct which we cannot avoid in aqueous solution. So that's something which it formed. And this, what we have found was, when you deposit more and more copper, you are able to increase the methane selectivity. So that's converting carbon dioxide into methane. Similarly, what we also found was, when you have a mixture of metal and an oxide, so your selectivity is slightly higher. So that's something which we found out. So, and that we usually people take some copper foil and they put it in the oven and then leave it for some 8 to 10 hours at some particular temperature, and they convert copper into copper oxide, and then we use that as an electrode material. So that's something people do. So what we did is, we took a copper foil, and we used a Bunsen burner, just put a flame and you just keep that electrode for 2 minutes, and you convert that into oxide, and then you can use that as an electrode or a catalyst for it. So in that way we tried. So this is different ways in which we had a powdered copper, metallic copper, and then we have copper at powder copper at copper 2 state. And we did a lot of experiments to find out, and then we are able to see that when you have a copper which is flame oxidized, they are giving same performance. Like there is a slight difference is there, but the performance wise is almost similar. So we got ethane and ethylene has 2 products. So this is the flame oxidized copper, and this is the conventional copper which is oxidized using a furnace, where within 2 minutes you can able to get a similar performance, where you have 8 hours of heat treatment as a material is subjected to. So that's something which we are able to get. So these are some demonstration to show that, we are able to convert carbon dioxide into some fuels. And as I said, the hydrogen evolution is one of the major problem we have when you pass carbon dioxide and you apply a potential. In addition to water reduction, hydrogen reduction evolution will happen. And so what we have done is, we have deposited some zinc. Zinc is one material where hydrogen can be suppressed. So we deposited different concentrations of zinc. This is a low concentration, 0.6 molar was used for deposition. We used a high concentration, 6 molar was used for deposition, and we get some different structure based on how you deposit on the copper. So you have a copper substrate deposited by zinc at 2 different concentrations, and here you can see when you compare. So the hydrogen, so this is the hydrogen which is there. The one of them has higher zinc content, one of them has lower zinc content. So when the zinc content is higher, the hydrogen evolution is lower. Like, by changing your material composition, you are able to reduce the amount of hydrogen which is being evolved in this process, and thereby you can increase the selectivity. In this case, methane and ethane selectivity could be. So this is more methane is formed, and you can increase the methane selectivity. Okay. So this is one way. So you can have different catalyst in which you can modify them by different way. Either you deposit to increase your surface area, or you deposit a second metal, or you make it as an oxide. So you are changing the surface property of the catalyst to improve the selectivity or increase the conversion of CO2 into some product. So that's the attempt we have been doing. And moving forward, so all those were gaseous products. We are looking at methane, ethane, and ethylene, and so on. So then we thought, when you have a gaseous product, it's a little difficult to separate. When you have, so then you need other process to again gas separation and so on. So then we thought, why not we have convert that into a liquid product. So liquid product are easy to separate or easy to get it. You don't need a storage and all is not needed. So then we attempted to convert that into formic acid. Formic acid is one of the building block which is widely used in chemical industries to convert or into other products. So we wanted to get into a liquid product where so we had a copper mesh, similar copper mesh was taken, and this is a process in which we made this copper into a copper foam. So you have a copper, flat surface of a copper that is made into copper foam, and over which then we deposit a catalyst. So a catalyst like tin, bismuth and indium were deposited on this. So all this were done in an electrochemical process. So if you look at, there is no high temperature, no high pressure, it's all done at ambient condition. You have aqueous precursors, you have aqueous solution where these precursors are dissolved. You apply a current or a potential where you can deposit these metals onto this substrate, and that is then used as an electrode for CO2 reduction. So then you put it in another cell. So this is done in a single cell, what we call as a single cell. Then you have an H cell where you separate the anode and the cathode. This is where carbon dioxide is passed into, and you apply potential and you reduce it. This is a counter reaction which will happen. So this is a configuration which we have done. So we started with, as I said, we have a copper substrate. We apply a current to make it into a foam. And this process is called hydrogen bubble template method, where in aqueous solution, when you pass high current, hydrogen bubbles will form, like your water, hydrogen from water will come, and that bubbles will create a space which will make it as a foam. Okay, so this is a mesh you can see, or this is a foil. When we make this, this is a foam. So this is highly porous, and the surface area is also very high. So you convert a mesh or a foil into a foam, and that's the first process we have done, where we increase the surface area, and on top of that we have deposited a catalyst. So you have copper substrate in which a copper foam is made, and on top of it we have either a nickel or a bismuth or a tin or a indium is coated on this one. So that is the electrode what we have made. And so these are some pictures to show, same pictures to show, you have a copper electrode with different magnification. Then we have bismuth deposited one, copper deposit, so tin deposited, bismuth deposited, indium deposited. We have deposited 3 different materials on this copper foam, and we will be testing them for the electrochemical experiments. And we also confirmed the presence of bismuth, tin and indium by EDAX analysis and also by XRD analysis. So we have done XRD to confirm, there is a presence of, so here you can see tin is there, indium is there, bismuth is there, which are deposited on the copper film we have. And then we did some electrochemical experiments. So these are called cyclic voltammetry experiments. The cyclic voltammetry, it's like your SEM for seeing the image. Cyclic voltammetry is a technique where you can see whether a material is having good activity or not, whether it is having a good catalytic activity or not. Okay. So you don't need to understand fully on the process. Higher is your current density. In this case, it's a reduction current. Higher is your value, better your catalyst. So that's the data you can get from cyclic voltammetry. So you run this experiment to find out. Here you can see the blue one has a better catalyst compared to the other two. So here if you look at, you can get current density as high as 80 milliamp per centimeter square. You can get 80 milliamp for a copper foam which is developed on a mesh. So like that. So we have done for different catalysts to find out which one is best. And so higher is your current density, better is your catalyst. So we have screened. Usually it is a screening technique. When you have 10 materials, you can do a cyclic voltammetry to figure out which one gives the best, which is the best catalyst. And once we screen them, then we apply this potential. So here we have different potentials. You apply a particular potential, then you apply for 1 hour or a 2 hour, and then you monitor the product, how much product is formed in 1 hour and 2 hour, like that. So like that we have done for 1 hour. So we applied 1.4 volt So here the four materials are compared. You have a bare copper mesh, then you have a tin deposited one, bismuth deposited one, indium deposited one. So here you can see higher is the value, higher is the Faradic efficiency. Like here we are looking at formic acid as a product. So more formic acid is formed in this condition at 1.6 volt, close to 80% Faradic efficiency is there, and both catalysts are good in this case. And so like that we have done for different catalysts, and we have characterized them to find out which is the best catalyst which we can use it for formic acid production. And we've also done some more electrochemical studies where this is a confirmation to say this is a foil, and this is the after a foam is made. So this is the copper mesh as such, and this is copper mesh on which the foam of copper was made. So you can see there is a change in the slope or a change in the value, which indicates that this has a high surface area compared to the, we call this as an electrochemical surface area. So it has a high surface area compared to the copper mesh. So that means this can give high activity. So earlier, if I go back, there is a change in activity between the regular one and the deposited one. The base substrate itself, since it becomes a foam, it has a high surface area. That is one reason. And conductivity also changes. So this is an impedance plot where smaller is the value, better is your conductivity, because when you have a large circle, your resistance is high. So you need to see low resistance. So these material like mesh, which is the copper foam, which was made, has a low resistance, and they are better compared to the one without foam in terms of conductivity. So we have made a material with high surface area and low or high conductivity, low resistance. So that is the base. That is one of the reason why the formate Faradic efficiency is higher. And we are comparing this. So I've taken one of the earlier slide to show. We have compared the same catalyst on two different meshes. One is on a foam, and then on a. So you have a substrate which is flat surface, another one is a mesh. So you are comparing two. The mesh has more porous, on that we have made a foam, so that is giving a highest Faradic efficiency. Close to 83% Faradic efficiency is obtained for a formate conversion. And we also looked at the stability, how long it can work without changing its performance, and where you can see that close to 8 hours the same Faradic efficiency is maintained. So the catalyst is stable for about this or some initial experiment. Later we have increased the hours. So it's stable. It has a high surface area. It has selectivity like 83% selectivity towards formic acid. So that's the kind of things we have got from here. And the one other thing what we have also done is, if you look at the industrial gas, you will not have pure CO2. So we'll have a lot of impurities. If you look from coal industry or any power plant industry, not just the CO2 will come, you will have SOx, NOx and so on. So other impurities will also be always present in this along with the CO2. So to mimic that, we have deliberately mixed SOx and NOx with CO2, and then we have done an experiment. Okay, so just to mimic the industrial condition. So we had chosen about 500 ppm of NOx and 800 ppm of SOx is mixed along with carbon dioxide, and we just purged into the solution, and then we have done experiments. So typically in catalysis, we call it a catalyst poisoning. That is, if you use for a longer time, so some things will accumulate on your catalyst surface, and that will block the active sites, and thereby your performance will decrease and your catalyst will die at some point of time. That's why you have catalyst regeneration process, or you need to activate the catalyst after some time and so on. So that can happen. So we wanted to see our tolerance to impurities, the catalyst what we have developed, we wanted to see the tolerance level. And so we had the same catalyst, if you remember. So the way we have done experiment is, first take a solution, purge with CO2, then apply the voltage and reduce it to formic acid. So the Faradic efficiency is 80%, and to the same solution we have purged NOx, saturate with NOx, and then perform the experiment. Then again, when the reduction is complete, you again pass carbon dioxide, do the experiment, then again pass NOx. Every half an hour we change, like you introduce NOx and you not introduce NOx. So if you look at the performance, so this is for the tin catalyst which is deposited on the copper foam. There is no change in the Faraday efficiency. So whether you have an impurity or not, the Faraday efficiency remained almost same. So that means the catalysts were tolerant to these poisons. So whatever we have NOx, it is tolerant. So we did the same for SOx. So first with NOx, next with SOx, then also with the mixture of both SOx and NOx. So both SOx and NOx were mixed along with the CO2. Then the reduction experiment was performed. And in most cases, you can see there is no change in the top value. So it is within the error bar. You can see it's all about 80% is the Faraday efficiency, where your 80% current is utilized to convert carbon dioxide into formic acid. And so there is no change. This is for the tin catalyst, and we did the same for bismuth catalyst. So bismuth also gave a very similar performance. So both were, so we were able to get two catalysts where they had a very similar performance. And then we did a, so this is just to comparison, we did a stability test, how long it can work. So we started with the, so if you look at the pure CO2 and the one with CO2 plus NOx and SOx, there was not much difference. They were almost similar, even for 7-8 hours. Initially we started for 8 hours, and later we have improved that to close to 50 hours. So this is a 50 hours data. So we have done this experiment for 50 hours where you pass carbon dioxide in one of them, or carbon dioxide plus SOx plus NOx, and you can see the Faraday. So there is some minor variation that's is expected, but overall the Faraday efficiency is close to 80%. So there is no change in the Faraday efficiency for over 50 hours. So this is for the bismuth catalyst. We did the same for tin catalyst, but tin catalyst was stable only up to 20 hours, whereas the bismuth catalyst stayed as a stable catalyst close to 50 hours with no decrease in performance. And so this is one of the good one. We have patented this work, and we have also just, it was published couple of months back. One of my PhD students, Sivaram, I think he worked on this, and we published in ACS Applied Materials and Interfaces. And the plan now is to, whatever we have done in the solution, we wanted to put it in a, like an electrolyzer. You just pass CO2 and then you get formic acid. That's the thing we wanted to get into. So we have made this electrolyzer. So where the cell is there, yeah. So this is the cell which is expanded in here. You have an anode and a cathode. In between there is a membrane. So your carbon dioxide is passed in one direction, and then at the output you should get formic acid as a product. So you'll have carbon dioxide going in, and when you get out you can get as a formic acid as a product. And so we can do that for direct CO2 passage, or we can also saturate the CO2 in water and pass the water for reduction. Both ways we can do, both way we are trying. So this is a cell which is about 6 by 6 centimeter square, 36 centimeter square cell we have developed. And we want to test, earlier it was just an experiment. It's a where you pass CO2 and analyze one by one. Here we wanted to continuously feed the CO2, and so that's more of a batch reactor. This is a continuous reactor. You continuously pass CO2 and you should be able to get formic acid continuously. So this is an ongoing work which we are working on, and hopefully maybe another time when we will have some data from such an experiment, but it's an ongoing work as of now. Yeah, so that is what I wanted to bring in here. So our idea is to capture, we don't work on the capture, but my colleagues who work on the capture will capture the CO2 and give it to us, and we will utilize that CO2 in the electrolyzer, and this electrolyzer is being powered by renewable energy. So we also setting up, we have a solar panel. So in the NAC building, so we have some solar panels which are powering the electrolyzer what we have. So we have a setup, so where the power to the electrolyzer is coming from the solar panel, and so we are continuously passing this CO2, and so we have a electrolyzer with catalyst which converts the CO2 into products, and then hopefully we are trying to get some, as of now, it's in the aqueous solution, we have formic acid, but we can also get other products. Like the other project which we are working on is methanol and ethanol. So you're converting CO2 selectively into methanol, or CO2 into selectively into ethanol. So ethanol is again, it's a biofuel which is used in, as an additive to petrol and industries, so on. So this is something which we are working on. And once we have a fuel, either it is a formic acid or a methanol or ethanol, can also be used as a fuel in fuel cells. So we also work, the other area of our work is fuel cells. You can feed that instead of hydrogen, you can feed the fuel directly. You can send methanol, ethanol, or hydrogen, in this case methanol or ethanol, and then the fuel cell will convert that fuel again into electricity, and we can use that. So that this is again a circular economy where CO2 from the vehicle industries, or from power plants, or which is coming out of the fuel cells, can be captured, send it into the electrolyzer, and convert back into fuel. So that's the kind of an area which is powered by a solar energy. So looking at a carbon neutral economy, so where you close the loop by not letting out carbon into the atmosphere, but you try to capture and use it with it. I think what we have done is in a very small scale, in a very what we call as a head cell level. Now we have just moved on to the what we call as a next stage, which is a slightly bigger cell. It's a pilot scale is still a far away. It's from a head cell to flow cell we have gone, but we need so this is system integration is something which we are working on, and the MEA type is the one which we are currently looking at. Like you have like an electrolyzer, you just pass hydrogen or water, you get hydrogen. Like that, you pass CO2, you should get ethanol, methanol, or formic acid, depending on the catalyst what we use. And so if this is proven, and it's like a it's electrochemical CO2 conversion, it should get you any product where we want. And similar to how we get hydrogen, we should get formic acid or methanol or ethanol from CO2 in distant future. That's all we have. We have published a review article on converting carbon dioxide into alcohol. I didn't talk about alcohol today, but I spoke only on formic acid. But this is an ongoing work which we are looking at, as we are working for an industry to convert CO2 into alcohols. Converting into formic acid is very easy because you have only 2 electron process, whereas converting into alcohol you need 6 electron. If it's methanol is 6 electron, if it's ethanol is 12 electron, which is very challenging. It's not that easy. And the Faraday efficiencies will go very, very, like right now we are getting close to 80, but it will go 30 and 20 like that. So it's a challenge. It's not that easy. There are a lot of challenges are there. So but as a R&D challenge, when we work as a researchers, always want to work on challenging problems. So that's what our students are doing. 2 are PhD students, Pooja and Sivaram, and Alamero is a postdoc. I think they're all working on this. So Sivaram has just finished, and he joined as a postdoc in one of the universities in the US. This is our group. Most of this work was done by Sivaram. Then we also have Pooja, who is now continuing with whatever Sivaram has done. So with this, I would like to thank you, and if you have any questions and comments, I would be happy to answer.